Okay, good morning, everybody. We're gonna talk about deadlocks. Um, I'm Aditi. I'll sort of introduce the concept of deadlocks and everything. So, first of all, we shared some resources on deadlocks here, like online reading materials and YouTube. Somebody also made a game, so yeah, that's interesting. Also, hope you can appreciate the pun. Anyway, so what is a deadlock? A deadlock is a situation where two or more processes wait for a resource that is being assigned to some other process. Like we can see through this graph, process one is waiting for resource two when it already has resource one, and process two is waiting for resource one when it has resource two. So they're sort of like stuck in an infinite loop here. And why do deadlocks show up? So to understand this, we have to dig a little bit into the concept of semaphores. So we know that semaphores are like the solution to the critical section problem. So yeah. So initially, semaphores function on the concept of busy waiting, but then what happened was processes just kept spinning in idly when they were waiting to get into the critical section. So this was like a waste of CPU cycles. So to counter this, we had the wait queue. We had the concept of wait queue where a process can block itself and then it has to wait for another process to give the signal operation. So what happens here, there's a problem here. So that problem is how deadlocks show up. Oh, okay. Yeah. So deadlocks and starvation. So when the implementation of semaphore with a waiting queue, this may result in a situation where two or more processes are just waiting for an event that can be caused by only one of the processes. So like it has to, a process A has to wait for process B to relieve it, but then process B can only happen when process A gives a resource. So that's what a deadlock is. And then the difference between starvation and deadlock basically is that in starvation, a low priority program can never get executed because priority program just keeps using up the resource every time. So it's an indefinite process. So it has to wait, but it's not an infinite process like a deadlock is, where you can't really do anything about it. So we can understand the concept of deadlock using a classical problem called the dining philosopher's problem. So basically, it's a very lengthy problem, but the gist says there's like a group of philosophers sitting on a circular table, and they have two states called eating and thinking, and they when they think they don't eat, so obviously, and then when they have to eat, they pick up a chopstick placed right next to them. They can only pick the ones placed right next to them. So when they pick it up, so oh wait, I'm sorry. Okay. Okay. So they can only use the chopstick that is to their immediate left or right. So there's a chance of deadlock happening here when everybody picks up the chopstick at once. So this is like the classic problem used to demonstrate a deadlock, which is not very relevant right now. Why don't they just talk to each other? Mhm. So let's look at some modern day examples of what a deadlock is like in our everyday life, like the job experience syndrome, when companies ask you to have experience, but then you just say, I will have experience if you give me a job. So that's a deadlock there. And then there is this ask mom, ask dad problem when you ask your dad for permission, and then he says, ask mom, and then mom just says, ask dad. So that's a loop there. And then when they're two shy introverts crushing on each other and then they just wait for the other person to tell that they like each other but nothing's happening, so it's like an endless loop and it's just nothing happens. It's a waste of time. So that's basically what a deadlock is. And is this useful anywhere? No, deadlocks are not useful. This is like an actual screenshot of me, of my Google feed, when I said where are deadlocks used, and Google broke down. So we know that deadlocks have no use. So we need to understand how they form, and we have certain methods of how we can prevent a deadlock from occurring. And yeah, so how do we find a deadlock? So we've been discussing about.
Sorry to interrupt, Aditi. So, can you go to the last slide? This example seems really interesting. Can you like explain it a little bit more? How did Google broke down because of deadlock?
Ma'am, no, it's I mean, I just said where it didn't break down actually, but like even Google had no answer for where are deadlocks used. So I just
Okay,
used
I
it.
got it. So this search query has no results as such.
Yeah, it has no results. Yeah,
All right, go.
yeah. So we've been discussing a lot about deadlocks, but the thing is, this is a very distant possibility. It's a very like it's an unlikely outcome, but it has a possibility. But it's more deadly if we find a deadlock, because we've never known how to deal with it. Our major strategy with deadlocks has always been the deadlock ignorance. So we just build our systems around ignoring the possibility of deadlock. But there are other methods too, which we will discuss, which Jayant and Drishti will discuss about. So yeah, that's my part. Thank you. um, I think Jayant has to do this.
Aditi, can you go to the next slide?
This is your slide, right? The next one.
Oh, no. Yeah, this slide. This slide.
Yeah,
Yeah.
okay.
Um, so deadlocks are like necessary condition. Necessary conditions are mutual exclusion, like when one or or resource is requested by more than one process, then it goes into deadlock. And hold and wait, like when a process is holding that resource and waiting for another resource, like it needs more than one resource, then deadlock occurs. And uh, this no preemption, resource cannot be taken from a process until the process releases the resource, like. And circular wait, so in circular wait, what happens is, even if when second priority process gets the resource, the first priority is not completed, so it goes on to the deadlock. I think next slide. So detection of deadlock. So when there is a when there is a resource and there is two instances, like two resources and two instances. In this case, this is for only one instance. In this case, if a cycle is formed, then it is in deadlock. like um, like in this diagram, process 1 is waiting for resource 2, but resource 2 is assigned to process 2, and process 2 is waiting for the resource 1. So as this is a cycle, the deadlock is formed. The next slide. So when there are multiple instances of resources, the detection of cycle is not so important. In this case, we detect it with the safety algorithm, or the banker's algorithm, and in that way we can find out. Next slide. So how can we recover the system from these, like the previous two conditions that we saw? We can recover it by killing the process, like killing all the processes involved in the deadlock in the cycle, in case if it is a single instance cycle. And the next slide. Aditi, can you go to the next slide? Yeah. So in this case, resources are previously handled. In this case, the resources are preempted, like they are given beforehand and to detect cycling or one second. Okay. So deadlock handling Drishti will handle.
Okay, so there are four ways how we handle deadlocks. One of them has been already discussed by Jen, deadlock detection. I'll be covering the rest. So, first method is deadlock ignorance. It is also called ostrich method. Aditi, next slide. Uh, so, some deadlocks occur once in many years, and developers don't focus on them because they occur very rarely. Instead, they prefer to focus more on hardware crashes and um system crashes and something like that. So we just ignore them, just like ostriches ignore sandstorm by putting their head in the storm until it's over, like ignoring the problem. Next is deadlock prevention. There are four necessary conditions for deadlock to occur, and if we prevent any one of those conditions, we'll be able to prevent the deadlock. So deadlock prevention has four methods: no mutual exclusion, prevention, preemption of processes, no hold and wait, no circular wait. Now we'll discuss each one of them in detail. No mutual exclusion. It means more than one process can have access to a single resource at the same time. It's impossible because it's multiple processes access the same resource simultaneously, and it will create a huge chaos. So no process will be completed because none of them will have a resource at once. So it's not feasible. Hence, the OS cannot avoid mutual exclusion. Next slide. Uh, To avoid hold and wait, there are many ways to acquire all the required resources before starting the execution. But this is also not feasible because the process will use a single resource at a time. Uh, the resource utilization will be very less, so thus hold and wait also does not is not feasible. Then next, the removal of no preemption. Uh, One of the reasons that causes deadlock is no preemption. It means CPU cannot acquire the resources from any process forcefully, even though that process is in a waiting state. If we can remove the no preemption and forcefully take resources from a waiting process, we can avoid the deadlock. So, if we end a process and provide the CPU to the other process whose resources are available by then, we can also avoid deadlock. Then next condition, sorry, removal of circular wait. Uh, the one of the necessary condition of deadlock is a circular cycle. So if two processes are stuck in the waiting state for the resource which have been held by each other, to avoid the circular wait, we assign the numerical integer value to all resources and the process has to access the resource in increasing or decreasing order. If the process acquires resource in increasing order, it will only have access to the new additional resource if that resource has a higher integer value and if that resource has a lesser integer value. It must free the acquired resource before taking the new resource and vice versa for decreasing order. I think for these the definitions are enough. Like there's nothing much to explain. Then we have next method, uh, deadlock avoidance. It has two parts: resource allocation graph and banker's algorithm. So in resource allocation graph, we have a pictorial representation of the state of the system, like what resources are required by what processes and what processes already have resources. So, um, Aditi, next slide. This is the example of single instance resource uh, allocation graph. We have two processes, R1 and R2. We have two processes, P1 and P2. So we can see the arrow pointing from R1 to P1 shows that R1 is already held by P1 and P1 is requesting for R2. So this is resource allocation graph and for multiple instances next. So here we can see that R2 has two resource instances and each of them are held by P3 and P2 and P1 is requesting it. In this case, we create a chart. Aditi, next slide. in which we tell which all processes are already allocated to which all resources are already allocated to which all processes, and which all are more needed for it to execute completely. And then the next part of deadlock avoidance is Banker's algorithm, which will be discussed by another team. That's it.
Okay, all right. Any queries, anyone? If you didn't understand something or if you want something to be repeated, do let me know. Okay, so if there are no queries, we'll stop here. You can use the remaining time for maybe just looking at some other videos on deadlock. So it can be a course related video, it can be one of the resources which Aditi pointed out. Aditi, can you paste those links in the chat window?
Yes, ma'am, sure. I'll share the slides here.
You can share the slides and you can also directly copy paste the link so everyone can just go there from the
Okay, ma'am,
link
sure.
itself, right?
Sure, yeah. Yeah.
All right. And then you can also watch the lecture video. So be sure that these three strategies are clear to you. So deadlock prevention. So prevention means that prevention is better than cure. You don't let deadlock occur at all. So you have your system designed in such a way that deadlock is not possible in such a system. So there you had four necessary conditions for deadlock. So even if you remove one of those conditions, your deadlock will not occur. But then removing those conditions, it will make your operating system inefficient, right? So then you had other strategies. So deadlock avoidance means, so two things, deadlock detection and deadlock avoidance. So deadlock detection means that you should have an algorithm which tells you that there is a deadlock in the system in case it is there. So one idea for that is detecting cycles in your resource allocation graph. So if there is only one instance of each resource, in case you have a cycle in that graph, it means deadlock is there and then you need to do something about it. You can decide what you need to do. You want to kill all the processes, you want to kill one process, so on and so forth. And then that's one, deadlock detection. Other than that is deadlock avoidance. So deadlock avoidance means you have certain numbers with you which you know, so what your process is they are going to demand in the future, and based on today's condition you can predict that in future there is a possibility of deadlock. If I allocate the resources in this particular way, a deadlock might occur, right? So you go around in the other way and then allocate the resources in that particular way. So that is your deadlock avoidance. So we'll talk about Banker's algorithm in the tomorrow's class. So if you have no queries, you can leave. If you have any queries related to any other topic also, you can stay back and discuss with me.
Okay, all right. If there are no queries, we'll end the session.
Thank you.
Thank you, Aditi.